Yes. A new, well, they say a new form of matter. Yes. They say that we know, we grew up in a time that there were only three states: solid, liquid, gas. Right. No, that's not true anymore. As of yesterday. I mean, getting your arms around just and this is amazing. This is just the beginning. If you read or heard about the Microsoft announcement yesterday, this is what life is going to be like multiple times a day in the next 3 years. This crystal isn't made of atoms. It's made entirely of electrons, and it formed all by itself at room temperature. A strange new magnetic material flips between order and chaos. Like it's half ice, half fire. And deep inside a quantum lab, time itself has started to crystallize. Across the world, physicists are stumbling into something they never intended to create. Exotic phases that might not just be strange but entirely new states of matter. And yes, some of these discoveries were never supposed to happen. In fact, one researcher said, "We thought it was a mistake." When physicist Svastik Kar from Northeastern University first saw electrons spontaneously organizing into a perfect crystal lattice between two thin sheets of material, he couldn't believe his instruments. His team checked and rechecked their data before accepting what they were seeing, something that challenges our fundamental understanding of how matter behaves. The discovery they couldn't explain. Imagine scientists studying what should be a routine experiment when suddenly their instruments show something completely unexpected. That's exactly what happened in the Northeastern University lab in 2020. We were simply layering two ultra-thin materials, bismuth selenide and a transition metal decalcogenide, when our instruments started showing something bizarre, explains physicist Svastik, who led the research team. What they observed defied conventional physics. The electrons, instead of spreading out randomly as they should, had spontaneously organized themselves into a perfectly ordered crystalline grid, a lattice made purely of electrons with no atoms involved whatsoever. Of course, we thought something was wrong, Kar admits. His team repeatedly checked their equipment, ran new tests, and verified their findings from multiple angles. The electron lattice was real. But here's what makes this truly extraordinary: it happened at room temperature. Most quantum phenomena require cooling materials to near absolute zero, where atomic movement nearly stops. This self-organizing electron crystal formed under normal conditions you'd find in your living room. After exhaustive verification, Kar finally acknowledged what they'd stumbled upon. I'm tempted to say it's almost like a new phase of matter. Think about that for a moment. We've all learned about solids, liquids, gases, and maybe plasma. But this is something fundamentally different. A geometrically perfect lattice emerging spontaneously, made not of atoms or molecules, but of pure electrons arranging themselves into a crystal-like structure. It's as if the electrons decided to play by entirely new rules of physics. If you're finding this fascinating, hit that subscribe button right now, because we're about to go even deeper into these accidental discoveries that are reshaping our understanding of reality. But if that shocked scientists, what came next may completely change how we think about matter. What if part of a material was frozen solid and the other part behaved like fire? The half-ice, half-fire paradox. Just when physicists thought they'd seen it all, researchers at Brookhaven National Laboratory made a discovery in 2024 that sounds more like magic than science. We were studying a one-dimensional fairy magnet when we noticed something that shouldn't be possible, explains the research team. Part of the material was behaving with perfect order while another part remained in complete chaos, simultaneously. Imagine a material that freezes and burns at the same time. That's not science fiction. It's lab-tested, and it might power quantum devices of the future. Here's what makes this half-ice, half-fire state so mind-bending. In one domain, all the electron spins align perfectly, like soldiers standing at attention. This creates a cold, ordered state physicists call the ice component. But in the adjacent domain, electron spins remain completely random and disordered, like a crowd in panic. This is the fire component. The material doesn't gradually transition between these states. It flips between them at a precise boundary. And when it does, it creates a massive change in magnetic entropy, essentially releasing or absorbing heat energy in an instant. What makes this especially exciting is that, unlike many quantum phenomena, this isn't just a physics curiosity. The researchers have already identified practical applications. The sharp phase switching could revolutionize refrigeration technology through magnetic cooling, more efficient than traditional methods. Even more intriguing, the distinct ice and fire states could function as the zeros and ones in a new type of quantum memory, potentially transforming computing as we know it. Understanding these mixed spin states could lead to great advances in quantum computing and spintronics. One researcher noted, This accidental discovery might become the foundation for technologies we've only dreamed about. If you want to see more stories where science stumbles into the unknown, hit subscribe. We break down the stuff they don't talk about in school. The hidden states ladder. For generations, we've been taught there are just a handful of states of matter. Solid, liquid, gas. Maybe your teacher mentioned plasma. And if you were lucky, they mentioned the Bose-Einstein condensate, officially recognized as the fifth state when scientists created it in 1995. But what if that's just the beginning? What if we're climbing a ladder of states that extends far beyond what we imagined? We're seeing a cascade of discoveries that don't fit neatly into our traditional categories, explains one physicist. Each one challenges how we define a state of matter itself. Consider the supersolid, a paradoxical phase that's simultaneously rigid like a solid yet flows without friction like a superfluid. In 2024, researchers in Innsbruck, Austria, finally provided direct proof of this dual nature when they observed quantized vortices, tiny tornadoes that only form in superfluids, appearing in a crystalline material. Or take time crystals. Unlike normal crystals that repeat in space, these repeat in time, essentially creating structure in the fourth dimension. Stanford and Google researchers used a quantum computer to create one in 2021. And just this year, Washington University scientists announced a time quasi-crystal with non-repeating temporal patterns. Then there's liquid glass, where particles flow freely but their rotations remain frozen. The Bose glass, where particles remain stubbornly localized despite quantum rules saying they should move. The Chiral-Bose liquid, with its magnetically ordered edge currents emerging from quantum frustration. Each discovery expands our understanding of how matter can organize itself. But this raises a provocative question. Are we being too cautious in our classifications? If these phenomena had been discovered in 1905 during the revolutionary period of quantum mechanics, would we already teach them as the sixth, seventh, or eighth states of matter? Asks one theoretical physicist. Or are we so specialized now that we hesitate to redraw the fundamental map? The boundaries between established science and new discovery have always been fuzzy. Even plasma wasn't widely recognized as the fourth state until the mid-20th century, despite being the most common state in the universe. What we might have missed. In today's research labs, data isn't just collected, it floods in. A single quantum experiment can generate terabytes of information, far more than any human could manually analyze. The sheer volume of data we produce is staggering, admits a physicist from MIT. We're generating more information in a week than entire physics departments produced in a year during the 1990s. This data deluge creates a fascinating possibility. What if new states of matter have already been discovered, but no one noticed? Emergent behaviors can go undetected for years, warns a Stanford researcher. Patterns that don't match what we're looking for often get filtered out as noise or experimental error. This isn't just speculation. Multiple research teams at institutions like MIT, Stanford, and Google are now deploying sophisticated machine learning algorithms specifically designed to hunt for phase anomalies in existing datasets. Unexpected patterns that human researchers might have overlooked or misclassified. We're teaching AI to look for what we don't know to look for, explains one data scientist working on the project. It's searching for the unknown unknowns. What makes this especially intriguing is the parallel track of classified research. For decades, agencies like DARPA have funded extensive studies into exotic quantum phases and topological matter, often for potential defense applications in computing, communications, and sensing. These programs have produced breakthroughs in superconductors, quantum computing, and metamaterials. But they've also generated vast repositories of experimental data, much of which remains classified or unpublished. If classified research encountered some of these exotic states first, would we even know? Asks a physicist who previously worked on government-funded projects. There's always a gap between what's published and what's discovered. This isn't conspiracy theory. It's the reality of how cutting-edge physics operates at the intersection of academic and national security interests. Before we wrap up, ask yourself this. If we already created new matter by accident, how many more discoveries are still sitting on hard drives, unnoticed? Global discoveries, the cascade of strange states. It's not just one lab or one lucky accident. Across the globe, the floodgates have opened to a cascade of exotic states that defy our textbook understanding of matter. In March 2025, Washington University researchers announced the creation of a time quasi-crystal. Unlike regular time crystals that repeat perfectly, these create non-repeating temporal patterns, structure that flows through time without ever exactly repeating itself. It's an entirely new phase of matter, declared Professor Zhu from the team, as they drove spins in diamond with microwave pulses to achieve this temporal fingerprint. Meanwhile, at Florida State University, physicists studying twisted 5-layer graphene at temperatures just fractions of a degree above absolute zero observed something extraordinary: quantum Hall liquids flowing through what they poetically called glaciers of pin charges. A system simultaneously behaving as both liquid and solid. Travel to Nanjing University and UMass Amherst, where in 2023 researchers engineered a frustration machine, a bilayer semiconductor where electrons and holes counterflow at equal speeds, giving rise to a chiral Bose liquid with magnetically ordered edge currents. At Cambridge, physicists created the first two-dimensional Bose glass, a system that refuses to thermalize normally and doesn't forget its details, violating some of the fundamental expectations of statistical mechanics. The University of Constance brought us liquid glass in 2021, where particles flow past each other like a liquid, yet their orientations remain frozen in rigid jammed clusters. And in Innsbruck, Austria, researchers finally provided direct proof of supersolidity, demonstrating a material that maintains rigid crystalline structure while simultaneously generating the quantized vortices that only occur in frictionless superfluids. One by one, scientists are unlocking material behaviors no textbook ever described. The pace is accelerating. The boundaries are blurring. And with each discovery, we're forced to reconsider what state of matter really means. Classic recap: what is a state of matter really? Now that we've explored these extraordinary discoveries, let's take a step back and examine what actually defines a state of matter in the first place. Traditionally, a state of matter represents a fundamental way that particles organize themselves with distinct physical properties and behaviors. The classic states, solid, liquid, gas, and plasma, differ in their density, particle arrangement, and how strongly the particles interact with each other. In solids, particles are tightly bound in fixed positions. In liquids, they flow while maintaining consistent volume. In gases, particles move freely with no fixed structure. In plasma, electrons separate from atoms, creating an ionized, electrically conductive substance. But there's an important distinction between a state and a phase of matter. A phase is a specific form a material takes under particular conditions, while a state represents a broader category of behavior. For instance, ice, water, and steam are different phases of H2O, but they represent the solid, liquid, and gas states, respectively. The fifth recognized state, Bose-Einstein condensate (BC), has an interesting history. It was theoretically predicted by Einstein and Bose in the 1920s, but wasn't experimentally created until 1995 by Cornell and Wieman at the University of Colorado. They cooled rubidium atoms to just a few nanokelvin above absolute zero, causing the atoms to collapse into a single quantum state, essentially behaving as one giant atom. This discovery earned them the Nobel Prize and opened the floodgates to quantum matter research. But it also revealed a classification problem that persists today. The challenge with quantum materials is that they often exhibit properties of multiple states simultaneously, explains one physicist. Our classical categories start to break down at the quantum level. Take supersolids. They maintain rigid structure like solids while flowing without friction like superfluids. Or time crystals. They're structured not in space but in time itself. These don't fit neatly into our classical understanding. This is why scientists are often cautious about declaring new states of matter. Instead, they typically describe these discoveries as novel phases or exotic quantum behaviors, at least until consensus builds within the scientific community. Science moves forward through both revolutionary leaps and careful incremental steps, notes one researcher. The exotic phases we're discovering today might eventually be recognized as fundamental states, or they might be understood as fascinating variations within our existing framework. What's certain is that we're pushing the boundaries of what matter can do. And these explorations are revealing a universe far more complex and beautiful than we ever imagined. So, have we really created a new state of matter by accident? Maybe not just one, but several. Whether we call them phases or states, one thing is clear: nature still holds secrets. And sometimes science discovers them without even trying. The electron lattices that formed at room temperature. The half-ice, half-fire magnetic phases. Time crystals that break symmetry in the fourth dimension. Each of these pushes our understanding of what matter can do into uncharted territory. What's most remarkable isn't just that these discoveries happened, but that many weren't even the goal of the experiments. They emerged unexpectedly, forcing researchers to question their assumptions and expand their thinking. As one Cambridge physicist noted, There are many things we still don't understand about how particles interact to form these exotic phases. The discoveries we've covered represent just the beginning of what might be a fundamental reshaping of our material science textbooks. These accidental breakthroughs remind us that the universe doesn't conform to our categories. Our categories must evolve to match what we observe in nature. And with every unexpected result, we get closer to a deeper truth about the physical world. Whether future generations will learn about 6, 7, or a dozen fundamental states of matter remains to be seen. But the journey of discovery continues, driven as much by serendipity as by design. If that fascinated you, hit subscribe.